A blade made from tungsten carbide, one of the hardest materials on Earth, takes a single strike against a medieval steel sword. The tungsten blade doesn't bend, it doesn't dent, it shatters into pieces like glass. The steel sword has a small nick in the edge and keeps working. This isn't theoretical. This is what happens when you try to improve on 3,000 years of sword metallurgy using modern materials. Today we're destroying the myth that modern metals are superior and revealing why ancient steel swords represent an optimization that modern metallurgy still can't beat. The modern material trap. We have access to materials the ancient world never dreamed of. Titanium alloys used in fighter jets. Tungsten carbide that cuts through steel. Tool steels harder than anything medieval smiths could create. Aluminum alloys stronger than bronze. Stainless steel that never rusts. Look at those properties and the conclusion seems obvious. Modern materials should make superior swords. We have stronger metals, harder metals, lighter metals, more corrosion-resistant metals. Ancient smiths worked with primitive materials and primitive techniques. Modern metallurgy should dominate. Except it doesn't. Not even close. And understanding why reveals something fundamental about what actually makes a sword work. Tungsten. When hardness kills. Tungsten has a hardness of 7.5 on the Mohs scale. Steel is 4 to 4.5. Tungsten's tensile strength reaches 1,510 megapascals. High carbon steel maxes out around 1,000. By every numerical measure, tungsten should make better swords. Strike a tungsten blade against a hard target and it fractures catastrophically. The blade shatters because tungsten is brittle. Hardness and toughness are not the same thing. Hardness resists deformation. Toughness resists fracture. Tungsten has extreme hardness and terrible toughness. Steel blades can have edge damage, nicks, even small cracks and keep functioning. The metal's ductility prevents cracks from spreading. A tungsten blade with equivalent damage just breaks apart. In real combat, it would last one engagement, and the weight makes it unusable anyway. Tungsten is 2.45 times denser than steel. A long sword that weighs 1.5 kilograms in steel weighs 3.7 kilograms in tungsten. That's over 8 pounds. Try fighting with that for more than 30 seconds. Your arms give out, your strikes slow, you're dead. The hardest practical metal on Earth makes terrible swords because hardness alone is worthless. Titanium, too light to cut. Titanium alloys are the opposite problem. Modern titanium alloys have excellent strength-to-weight ratios. They're used in aircraft, spacecraft, and high-performance applications where weight matters. Titanium is 45% lighter than steel with comparable strength. This sounds perfect for swords. Lighter means faster, easier to wield, less fatigue. Make a titanium sword and you should dominate heavier steel blades. Except swords need mass. Cutting power comes from mass times velocity. A lighter blade moving at the same speed delivers less impact energy. You can swing faster, but the reduced mass means you're still delivering less cutting force overall. Worse, titanium can't hold a sharp edge like steel. The same properties that make titanium tough and light make it poor for edge retention. Titanium dulls quickly under cutting stress. You'd need to resharpen constantly, and even then, the edge geometry can't match steel. And titanium is expensive. A titanium sword would cost 10 to 20 times more than an equivalent steel blade. In any era where you're equipping armies, that economic reality alone disqualifies titanium. Modern metallurgists have created titanium that outperforms steel in aerospace applications. But aerospace requirements and sword requirements are completely different. Titanium optimizes for the wrong properties. Modern tool steels. Optimization for the wrong job. Modern tool steels can reach hardness levels ancient smiths never achieved. M2 high-speed steel can hit 65 to 66 Rockwell hardness. D2 tool steel reaches 60 to 62 Rockwell. These steels are designed to cut metal, withstand high temperatures, and maintain edges under extreme industrial use. Make a sword from D2 tool steel and you get an edge that stays sharp longer than any medieval blade. That edge will also chip and fracture the moment you hit something hard at the wrong angle. Tool steels achieve extreme hardness by sacrificing toughness. They're designed to operate in controlled conditions, cutting in one direction against stationary materials. They're not designed for impacts from random angles during chaotic combat. Medieval swords used medium carbon steel, 0.5 to 0.8% carbon, hardened to 50 to 55 Rockwell at the edge. This seems primitive compared to modern tool steels, but that hardness range is optimal for swords. Hard enough to cut effectively, soft enough to flex without breaking. A sword at 50 Rockwell can bend 25 to 30 degrees and spring back straight. A tool steel blade at 65 Rockwell bends 5 degrees and snaps. Flexibility matters more than maximum hardness, because swords experience complex stresses from unpredictable directions. Modern tool steels are optimized for industrial cutting. Ancient steel was optimized for surviving combat. Combat won't let you control the angles or the forces. The blade needs resilience, not maximum hardness. Stainless steel. trading toughness for corrosion resistance. Stainless steel doesn't rust. It maintains appearance without constant maintenance. Modern stainless steel alloys like 440C can even achieve reasonable hardness, around 58 to 60 Rockwell. So why don't modern sword makers universally use stainless steel? Because the chromium content that prevents rust also reduces toughness. Stainless steel is more brittle than equivalent carbon steel. 440C stainless at 58 Rockwell is more likely to chip or crack than 1095 carbon steel at the same hardness. The metallurgical properties that create corrosion resistance compromise the properties that make swords survive impacts. Medieval warriors maintained their swords. They oiled them, cleaned them, prevented rust through care. This wasn't a flaw in the material. It was an acceptable trade-off for superior combat performance. Modern stainless steel optimizes for appearance and low maintenance. Combat swords need to optimize for not breaking when your life depends on it. Different priorities create different materials. If you're realizing modern doesn't automatically mean better, subscribe right now. Aluminum alloys, strong but soft. Modern aluminum alloys like 7075 have impressive strength-to-weight ratios. They're used in everything from aircraft to sporting goods. Aluminum is roughly 1/3 the weight of steel, but aluminum is soft compared to steel. Even the hardest aluminum alloys max out around 150 to 200 on the Bernal hardness scale. Steel reaches 400 to 600. You cannot create an aluminum edge that cuts like steel. The material is too soft. An aluminum sword would be extremely light and fast, but it couldn't cut effectively, would dent and deform easily, and would wear out rapidly. Against a steel sword, the aluminum blade would be destroyed in the first engagement. Aluminum optimizes for weight reduction in applications where cutting edges don't matter. Swords are fundamentally about cutting edges. The material fails the primary requirement, what ancient steel actually achieved. Medieval smiths working with medium carbon steel achieved something modern metallurgy hasn't surpassed for sword applications. They created a material that balances hardness, toughness, flexibility, weight, cost, and manufacturability. A properly made medieval sword with differential heat treatment has a hard edge around 50 to 55 Rockwell for cutting, a softer spine around 40 to 45 Rockwell for flexibility, and a core that prevents crack propagation. This combination creates a weapon that can cut through flesh and bone effectively, flex 20 to 30 degrees without breaking, survive edge-to-edge impacts without chipping, maintain functionality even with minor damage, be repaired and resharpened indefinitely, last for decades or centuries with proper care. No modern material achieves all of these properties simultaneously. Each modern metal optimizes for specific applications that aren't sword fighting. Tungsten for hardness in cutting tools, titanium for weight in aerospace, tool steels for industrial machining, stainless for corrosion resistance, aluminum for weight reduction. Ancient steel was optimized specifically for swords. 3,000 years of combat feedback refined the material properties to exactly what works. The result is a material that modern metallurgy can match but not beat. Why modern reproductions work. Modern sword makers do create excellent swords, but they use the same basic material as medieval smiths. Medium carbon steel, typically 1050, 1060, 1075, or 1095 carbon steel. Heat treated to similar hardness ranges. The same fundamental metallurgy. Modern improvements are in consistency, quality control, and manufacturing precision. We can create more uniform steel with fewer impurities. We can control heat treatment more precisely. We can produce swords faster and more reliably. But the base material is essentially the same. Because that material is optimal for the application, modern metallurgy hasn't invented anything better for swords because the original solution was already correct. What this reveals about progress. The inability of modern metals to beat ancient steel swords reveals something uncomfortable about technological progress. Progress in one area doesn't automatically translate to progress in all areas. We've created materials that outperform steel in countless applications, but those materials fail as swords because swords have unique requirements that don't align with modern industrial priorities. Ancient smiths didn't have access to our material science knowledge, but they had something just as valuable. 3,000 years of direct feedback from combat. Swords that broke got men killed. Swords that worked got copied and refined. Natural selection optimized the design. Modern materials are optimized through engineering for specific applications. Industrial cutting, aerospace structures, corrosion resistance. These applications have different requirements than swords. So the resulting materials, despite being objectively stronger or harder or lighter, fail when used for sword making. The uncomfortable truth. Ancient steel swords represent an optimization that modern metallurgy hasn't beaten because the optimization was already correct. Medieval smiths, through generations of trial and error and the brutal feedback of combat, created a material that balances all the properties swords actually need. Modern metals offer improvements in individual properties: harder, lighter, stronger, more corrosion resistant. But swords don't need maximum performance in one property. They need adequate performance in all necessary properties simultaneously. Steel achieves that balance. Modern materials don't. This isn't romantic nostalgia for the past. It's recognition that some problems were already solved optimally, and trying to improve them with modern materials just reintroduces problems that were solved centuries ago. The ancient world got sword metallurgy right, and sometimes understanding why ancient solutions work is more valuable than assuming modern must be better.